Got it? Think so?
Yeah.
All right. I will begin. Dear Father, we thank you for this day. Thank you for this semester. Just pray you help these students in this final exam week, that they just do their best, Lord. Give them energy to persevere and just keep at it. In your name we pray, Lord Jesus. Amen. So yes, the final exam week is upon us. Seems like just yesterday we were studying vectors, but I guess we never stopped studying vectors, really. But sometimes it seemed like that, didn't it? So this is your life in Calculus 3. We started with what? Talked about vectors, points, components, and we talked about dot products, angles, projections, the cross product, equations of lines and planes, curves and surfaces, curvilinear coordinates, calculus, curves, arc length, geometry, curve, 3D motions, the Fresnel array frame, the TNB stuff, the curvature, the torsion. We talked about how to integrate things with respect to arc length around curve. Then we talked about limits, open sets ever so briefly, directional derivatives, partial derivatives, chain rule, the gradient vector field, directional derivatives with 3 variables. I said a little bit about the general concept of differentiation. We talked about tangent spaces, how to find them, either parametrically or by equations. We talked about how to calculate the gradient and curvilinear coordinates a little bit. Never really pushed you too hard on that. We talked about Lagrange multipliers, talked about the multivariate Taylor expansion, second derivative test, the closed set test, and then we talked about multiple integration, double, triple, variable bounds, not variable bounds, switching the bounds, choosing cylindrical, spherical, or other coordinate change with respect to the Jacobian. And once we were done with that, then we turned the page to what's called vector calculus. In particular, we talked about divergence, curl, gradient, how to calculate the line integral, how to calculate the surface integral, Green's theorem, of course, how to characterize conservative vector fields, the Gauss theorem, the Stokes theorem, and that was it. So there you go. So you know all that, you're good to go. Okay, that was useless. But anyway, the point is, the final exam is comprehensive, and that's more or less what's on it. Yeah. Yeah. Not everything, though, obviously.
Dr. Cook, I saw on the schedule that since our class meets 5 days a week, there were 2 different test times on the final exam schedule. So, which one will be?
So I made an announcement a while ago that it will be from 9 till noon. So I give you guys 3 hours to do it on Monday. So technically, we have the 8 till 10 o'clock spot, and then we've got the 10:30 to 12:30 spot. So I just split the difference and said we'll just use 9 till noon. That way you have 3 hours and it should be good. Yep.
What if you have an exam that starts at 10:30?
That's impossible, because my exam, this class meets at the time which has a 10:30 spot.
Oh, no, at 8.
That's impossible because this class has the...
I have 2 exams.
It's not possible, because I have both of those exam periods. I have, in this class, since we meet Monday, Wednesday, Friday, 1:05 to 1:55, and then we meet Tuesday, Thursday, 12:45 to 2. Now, let me just check on it. I mean,
I realize my mistake.
that's okay, but it's worth checking on. So the reason I'm saying this is the final exam schedule. We're spring 2018, so we meet here, which means we've got that spot, and we meet here, which means we got that spot. So I just said, let's not meet at 8 because it's horrible, and so let's meet from 9 till noon, like civilized human beings have 3 hours for a final, which is how long you should have. We should have 2 hours for a final. It's crazy. But anyway, I always had 3 hours for my finals when I was an undergraduate. Every final I took was 3 hours. Why do you just have 2 here? It doesn't make any sense to me. Whatever. I can fix it for your class. I can't fix it for most. Yeah.
I was just going to ask, so I know you said it's comprehensive, the test, but
Uh-huh.
you were also saying earlier that like with the Gauss's theorem and Stokes, that that's kind of like the culmination of the course. So would you say that there might be like more of an emphasis on that?
I think there would be more of an emphasis on that. Here's a template that I'm going to hopefully fill out for the final exam. I mean, here's a sort of guesstimate of where I am at the moment. Problem 1, vector math. Like, here's 2 vectors. Find the angle between them, cross products. Maybe find the angle of the triangle that has A and B as sides. You guys taking pictures. It's funny. Problem 2, maybe something about a plane equation, like here's a point off the plane, how far is it from the point to the plane, you know? Directional derivatives, what was a typical directional derivative question? How about like, here's a function of x and y, here's a point, is it possible for this function to change at the rate of 13? What would you do then? You set the gradient evaluated at the point dot with AB equal to 13 and see if you can solve that equation subject to the condition that a and b, the a squared plus b squared is 1, right? Unit vector. And you know that if the magnitude of the gradient is less than 13, it's impossible. But if it's greater than 13, it is possible, and there will likely be 2 answers.
So you're saying that is what's going to be 1, 2, 3, 4, 5?
Possibly. That's where I am right now. I mean, I'm not done. It's possible. I mean, I may feel obligated to add a problem. I'm thinking about it, you know. This is my current draft. I can show you some past finals. Yeah, I can show you some past finals. No, they're not on my website, no.
For the, you said 300 points and bonus, will that be built in just like the
Yeah, this is a, again, this is a draft. I don't know if that's accurate to our syllabus this semester. I have to.
I think it's 240.
Yeah, that's okay.
Yeah, so this one should be out of 240. I mean, will there be a bonus question? Probably. Let's see here. But, you know, there's typical directional derivative optimization, something like I give you a function of several variables, I give you like a disk, or maybe a partial disk, say find the maximum, minimum of that function of 2 variables on the disk, or maybe a rectangle or something like that. Remember, it had 2 parts. We find the critical points inside, and then we either use Lagrange multipliers or restriction to test how the function works on the edge. Remember those problems like that? Of course, also, I might put a problem in which has got like second derivative test. You know, here's a function, find the critical points, and determine if at the critical points you have a local min, max, or neither. Right? We had those problems. Remember those? Chain rule. Well, there's lots of different chain rules to think about, but typically it's something like, you know, well, I have ones we'll look at in a second here, but there's lots of typical chain rule problems. We worked a lot of chain rule problems. That was like what, test 2? Yeah. I think I'm missing a problem here, which was, as I look at this, I realize I'm missing a problem. You're like, no! You're not missing anything. What about given velocity as function of time, find position and acceleration. All of these are vector valued functions of time, right? And for this problem to make sense, what else do I need? You can't find the position as a function of time, right? If I give you the velocity and you want to find the position, for example, it's been a while since we did this. Let me just write one out. Suppose I'll give you v of t, you know, t squared cosine t 1, right? If I say find the position, you should say, that doesn't make any sense, right? Unless I do what? What am I missing? What else do I need to tell you in order to find the position? What's that? No. Initial velocity, no. I can tell you the initial velocity is 0, 1, 1. Yeah. But you got the right idea. Initial position, or at least position at some time. Right? So supposing, let's say, r of 1 is 1, 2, 3. I need to give you that data. If I don't give you that data, you can't actually find the position, right? So how do you solve it? Remember that v equals to dr dt. So that tells me that r of t is 1/3 t cubed sine t, t plus some constant vector, right? Hence, r of 1 is equal to what? 1/3 sine of 1 plus that mystery constant vector. What is the mystery constant vector? It's minus the thing I just wrote down, right? Oh, I'm sorry. I can't do math. This is equal to what? 1, 2, 3, right? I gave that to us. So the c vector is 1, 2, 3 minus 1/3 sine of 1, 1. So that tells me, thus, the position as a function of time is, what is it? It is 2/3 plus 1/3 t cubed, 2 minus sine of 1 plus sine t, and where was I? Oh, t. And what do we got? We got 3 minus 1, which is 2, right? So there you go. That's the position as a function of time, given that the initial position at time 1 is 1, 2, 3. Right? So what I'm trying to say is this new problem 3 that I just annoyingly added to the list, it only makes sense if I actually give you the particular position at a particular time. Otherwise, you can at most find the position as a function of time up to some constant vector you don't know that describes the initial position. How do you find the acceleration, though? That's easier, right? Differentiate. The other kind of problem here that I've neglected to put in, which I should, because I might put that, is, what was the other kind of problem we worked in here? It's pretty common. Given the, path, find t, n, oops, can't type. I can't talk and type. So that was the other kind of problem that we had. And I think I put one of those on your test as well, right? Given a path, find the tangent, the normal, the binormal, the curvature, and torsion. So that was another very common problem type in that part of the course, right? All right, so past that, kind of turn the page to integration. Typical problem, like I give you the integral setup one way, you have to switch the bounds to do the integration, right? The way you do that is to write out the graph of what you're looking at and then like recharacterize from type 1 to type 2 or vice versa. And then we've had various center of mass problems, right? So it could be a center of mass in a plane or in a volume or on a surface or for a curve. There's really 4 different center of mass kind of problems, right? But how many 3x5 cards did I let you guys bring? 4. So you should have the center of mass formulas for each of those 4 types somewhere in those cards, right? You know what I'm talking about? What are the 4 different types? Just sketch it. So first of all, you could have center of mass of something just like a space curve, right? You could have center of mass of some kind of curvy thing. You could have the center of mass of a laminate, XY. Or you could have the center of mass of a, like, honest to goodness, 3-dimensional blarb. So integration, so here I'll write that formula for mass in each case. Here the mass would be the integral of lambda ds typically along the curve. Here the mass would be the integral of sigma ds along the surface. Here the mass would be the double integral of sigma dA along the region. And here the mass would be the triple integral of the density, what I use for density, delta? I guess I use delta. Delta dV over this solid region E, whatever you want to call it. Right? And then to find the center of mass, we integrate x, y, and sometimes z. Well, the only one where we don't find z is this case 3, this laminate. Z is equal to 0 here, essentially, in this discussion, right? When we talk about center of mass of like, here's a stupid one. You tell me. Constant density, what's the center of mass for a disk, radius 1? 0, 0, all right, yay. Okay, so I probably won't ask that, but, you know, maybe I might ask, what's the center of mass for this one, right? So then you kind of already know intuitively it's like here-ish, right? It's not halfway, right? Because wherever the center of mass is, if you were to draw this like dividing line, you should have an equal amount of mass above and below the dividing line, right? So where's that? Where do you have to put that line in order to get more mass above and below, just balancing out? That would be where, what's that? Yeah, it's got to be below a half. It's somewhere in here-ish, but 0, 1, oh, we already worked it out. Okay, good memory. But
Oh wait, is that right?
it might be. I don't know. I feel like there's probably a square root involved, but I could be wrong. Anyway, my larger point is that there's tons of center of mass questions which make interesting ways for me to test you on integration along an arc or a curve, right? The surface integral, and you know, or the triple or the area. I mean, this is just a basically invitation to test a lot of. We've had basically 4 different kinds of integration in that sense that we've done. All right, line integral. Right now, I'm mostly talking about test 4 stuff, right? So like line integral, conservative vector field, Green's theorem, divergence theorem, Stokes theorem. So you see, you know, 10 through 14 in my current allotment are on basically test 4, right? So test 4 does tend to get more strongly emphasized on the final for various reasons. So, I mean, that's partly in your best interest because you're actually most sort of in tune with that stuff because you just had a test on it, right? So you've got a good chance of fixing what you did wrong, hopefully, and you know, doing better on these questions on the final, for one thing. Anyway, any questions? I did say I'd look at an old final with you. You want that? Let's see here. So you got a choice. Do you want spring 17? Do you want fall 15, fall 14, fall 13, or 2011? 17. It's no fun.
What's the calculus 3 bailout?
Calculus 3 bailout. Huh. Bonus take-home work for test 2. So apparently I gave a test 2 that went very badly. And I punished them with this take-home. Oh my goodness. Ooh. Ooh. Yeah. Huh. Ew, look at that integration. That's just, oh man. Huh. Giving me ideas for your final. I'm just kidding. Just kidding. All right. Here we go. Let's see here. What's that?
I like the first problem. 20 points for that.
You know, I mean, I like it too, but you would be surprised how many people get that wrong. It saddens me, but it happens because people don't do one simple thing, which is check your answer. You take the dot product of the answer. If it's 0 for both of those, odds are very good you calculated it correctly, right? But if the dot product with either one of those is not 0 with your answer, you're wrong and you need to fix it. All right? Just saying. 3 points. Triangle has 3 points. Find the interior angle of the triangle at P. Find the area of the triangle.
Can you post this by chance? Or is this just right now?
I can post it if you want. No skin off my nose. Let's see here. I don't know, where's that saying come from anyway? No skin off my nose. Anyway. People regularly losing skin off noses or something somewhere? I mean, like, what is that about? I don't know. Let's see here. Find the point on the plane x plus 3y plus 4z equal to 128, which is closest to 3, 11, 10. How should you solve that problem? I would find I find the normal line, right? Which goes through the point 3, 11, 10, and then find where that normal line intersects the plane. What's the direction vector to the normal line? 1, 3, 4. Right, so I take something like t times 1, 3, 4 plus 3, 11, 10. That's my r of t, and then I set r of t. I plug r of t into the plane equation, right? The x part of it plus the y part, 3 times the y part of it plus 4 times the z part of it equal to 128. That will give me a particular time where that normal line intersects the plane. Then I plug that point back into the normal line. That gives me the point which is closest. And then to find the, oh, I didn't ask what the distance was from the point to the plane, but that's another question I often ask, is how far is the point off the plane, right? So if you find the closest point, then you find the distance between the closest point and the point off the plane. That would be the distance from the point to the plane. How do you do problem 4? So we know that the gradient of the level equation, x squared plus y cubed plus z to the 4th, this gives me a vector field, which is everywhere normal to the surface, right? So that's 2x, 3y squared, 4z cubed. And I'm asking for the Cartesian equation of the tangent plane at the point ABC. So I evaluate at ABC, and that gives me the normal vector is 2a, 3b squared, 4c cubed. Thus, 2a times x minus a plus 3b squared times y minus b plus 4c cubed times z minus c equals to 0. There you go. That's the equation of the tangent plane to that surface at ABC. Popular mistake you guys make is basically, instead of writing 2a, what I see a lot of students do is put 2x here, to put 3y squared here, to put 4z squared, 4c cubed there. They're like, that's the popular mistake. You guys do not evaluate the gradient vector field at the point of tangency. But that's so important, you need to do that, right? Just like in Calculus 1, when you're finding the equation for the tangent line, you have to plug in the point of tangency to find the slope of the curve, right? When you're in Calculus 1, I will say things like, I will try to berate you, like, you've given me a tangent line that's a cubic. How dare you? You know, because you haven't plugged in the point of tangency. You've just left it as a function of x rather than plugging in the point. That same thing is true here. We have to evaluate at the point of tangency. Yep. We take attendance. All right, now I have to count everyone at another attendance point. All right, so, curses. A reminder to self, +2 attendance for everyone. All right, thank you, Stacy. That helps get the daily quiz points up to where they need to be. That's definitely helping. So, man, see, I thought it was going to be an actual question, too. Like, my hopes get raised every time you guys do that. Like, it's such an emotional roller coaster for me. I'll get over it. I'll get over it. Let's see here. So 867 plus this plus this plus that is 0, 0 critical point. Yeah, because it's got no what? It's got no x or y terms, which we can read from that fx and fy at 0, 0 are both 0, which means that 0, 0 is a critical point, right? And then we can look at what's given, and we can read that fxx is 10, fxy is 30, and fyy is 18. Because remember, there's like a half with the fxx and the fyy term in the expansion. And so then you can go back to the big D test, right? Which is what? We do what? Fxx, fyy, minus fxy squared This is all at the critical point, right? I evaluate that at 0, 0. So what is that I just said? Okay, yeah, it's a 10 times 18 minus what? 30 squared. So that's what, 1800 minus, is that 1800? 180. 900, oh, that's less than 0. It's a saddle point, right? Because we learned if the big D was less than 0, it's a saddle point. If it's positive, it's either a min or a max, depending whether it's positive or negative, right? Well, depending on whether the second partial derivative with respect to x is positive or negative. If the second partial with respect to x is is positive, then it's a minimum. If the second partial with respect to x is negative, it's a maximum. Again, this should be on your card, right? The second derivative test. Yeah.
Wasn't there like a thing like if the x squared and y squared both positive, like you could say it was a min because like everything else was positive?
If x squared and y, if x, yeah, you can say that it's a min, but that there's strings attached. So, okay, so like for example, if I had f of x, y, z is equal to 10 plus x squared plus 3y squared plus 10z squared plus da 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 da. Yes, I could conclude that f of 0, 0, 0 equals to 10 is local min from that. But there's something important and different about the expression I just wrote versus what's in that problem. Namely that there is no cross term. There's no like xy or yz kind of term. Here, there's the pesky 30xy term. And see, that can either be positive or negative depending on whether x and y are both positive or both negative, or one's positive and one's negative. And so there's like a conspiracy of this is either taking away or adding to depending on which quadrant you're in. And the question is, this taking away or adding to process, does that win against this and that, or does it lose against this and that, depending on where you are? And that's kind of complicated to sort through just by sort of back of the envelope calculations. That's what the big D test is for, is it sorts through all that for us, because hidden within that's the linear algebra that's needed to unravel that question of whether or not the cross term wins or loses. So, in short, this spoils us from just looking at it and going local min. If there's a cross term, we have to fall back on the second derivative test. Now, if it's 3 variables and there's a cross term, I made a typo, because I wouldn't test you on that because that requires linear algebra. So 3 variable min-max questions I have to give you. I'm pretty much honor bound to give you things of the form sums of squares or all pluses, all minuses, no cross terms. All right, there actually is a way that I could put cross terms in a 3-dimensional problem and still make it reasonable for you guys, but I shouldn't do it. I should stop thinking about that. I should stop thinking about it. I'm trying to stop. Change the topic, quick. Okay, yes, this one. So here's that directional derivative problem I was mumbling about. Here's an example. The rate at which f is changing in the 3, 4 direction at the point 1, 2, how would you calculate that? That is the directional derivative of f at the point 1, 2 in the 3, 4 direction. How do you actually calculate that? There's a small but noticeable trap here. I said 1, 2, right? So we're supposed to take the gradient of f, evaluate it 1, 2, and take the dot product with a unit vector in that direction. So what's the gradient of f here? Looks like we got 2x minus 8y. Yeah. Plug in 1, 2. What we got? We got 2 minus 16. And we take the dot product of minus 3, 4. No, don't fall for it. That's not a unit vector. It's a trap, right? So I won't take off like all the points, but you'd lose about 20% here if you didn't normalize that vector, right? It's part of it. So normalizing that, we get minus 3/5, comma 4/5, because this is a vector of length 5. The square root of 9 plus 16 is square root of 25, which is 5. That's a vector of length 5. So to normalize it to length 1, I have to divide by 5. Ha-ha! Ha-ha. Yeah, sometimes if you grab your nose right before you're about to sneeze, you can stop it.
Isn't it really unsatisfying?
It is unsatisfying, but it is not as infinitely horrible as just trying to hold it in. But not successfully holding it and then like half sneezing while holding it in, right? That's the worst. You know what I'm talking about, right? You ever done it? It's horrible. Yeah. It's very horrible. Okay, anyway, sneezing, questions of sneezing aside. Let's see, minus 6 over 5, minus 4 times 16, 64 over 5, also known as minus 70 over 5. That feels like, I don't know, what we got here? I can't do math. Minus 14, thank you. All right. So there you go. That's the rate of change. That's the answer to part A. The rate at which f is changing in that direction at that point is given by the directional derivative. Don't forget, this has to be unit vector, right? So that, I'm not honor bound to give you a unit vector. I just have to give you a direction, right? Yep.
So that means like at that point you can have less than that, or you can have more.
Well, let's see here. The length of the gradient vector, right, is what here? Square root of 4 plus 16 squared, which is what? 196? I don't know. 256. I can't do math. All right, thank you. I feel better now. Or I feel worse. I definitely feel worse. Square root of 260, which is what? I don't know. 8? No, that's wrong. It's really wrong. Well, 15 squared is 225, right? Oh, it's very close to 16, obviously. Duh. So this is approximately 16.1-ish. I don't know.
Okay, so then that's the maximum.
That is both the max and the min. We have that the gradient, well, the directional derivative and the u-hat direction of f at the point 1, 2 is less than 16.1-ish and minus 16.1. I mean, that's it, because remember that this could also be written as the magnitude of the gradient at that point, right? Times the cosine of the angle. Right? So if you make them perpendicular, you get the rate of change of 0, right? If you make the angle 0, then you have the maximum rate of change. If you make it 180 degrees, you've got the minimum rate of change, the largest negative rate of change. But yeah, that's what you're stuck with, if that's the gradient at that point. Find the minimum and maximum values of f on the disk. Method of Lagrange multiplier. I'm bored. I don't want to do that. Let's see here. Suppose c is a constant vector and the velocity of a ninja is given by v of t is equal to t squared c. If the ninja is at 0, 0, 0 at time t equals to 1, find the position and acceleration at time t. Well, this is much more exciting than some stupid Lagrange multiplier problem. Let's see here. All right, so this is a little bit scary because I don't give you, the way I present the problem is perhaps a little bit weird to you. I mean, you could write this as t squared c1, t squared c2, t squared c3, and go from there, right? But I'm going to stick with this because it's a good way to think. So we've got, first of all, the acceleration is d dt of v, right? So that's d dt of t squared times c. Well, one of the things I would like you to have learned in the context of our discussion of the calculus of paths is that constant vectors behave just like constants, and you can pull them out of derivatives. So in fact, a rule of calculus in this context is that we can pull the c out, just like that. And the answer is 2tc. So there you go, that's the acceleration. Likewise, v is dr dt, right? But it's also t squared c vector. So if I integrate both sides, this gives me r of t is 1/3 t cubed c vector plus some other constant vector. We could call it, I don't know, b for lack of imagination, right? Now b is some constant of integration. I plug in time 1, I get 1/3 c plus b. What am I told that where's the position at time 1? 0, 0, 0. So that's equal to 0, 0, 0. So therefore b is minus 1/3 c. And so in summary, we get that the position at time t is 1/3 t cubed minus 1 times the c vector. Where there's a c vector on both terms. I just factored it out. And you can check my answer pretty easily. If we plug in time 1, we get 0. I now have done 2 of these. One with explicit formulas for your x, y, z components. This one now being a little bit more symbolic. Yeah. At some place on the test, I will test this kind of symbolic calculation. Not every question, but somewhere there's going to be this kind of calculation. Something where you're not given functions and you're supposed to work at a slightly more abstract level. This always appears somewhere on my final. Oh, here's that chain rule problem I was talking about, right? I give you z is tangent of x cubed plus y squared. I tell you x as it relates to alpha and beta. And I say calculate partial z, partial beta. And I say, please feel free to use x and y in your answer. That is an honest request. Because it's so much more pleasant to grade it if you use x and y as opposed to re-expressing the whole thing in alpha and beta. Oh. So partial z, partial alpha, how's that go? That's partial z, partial x, partial alpha, plus partial z, partial y, partial alpha, right? Now partial z, partial x, I can look at I get what? I get secant squared, well, excuse me, I get, I can't read, 3x squared. I decided to do this one. But it's fine. 3x, but you're right. You take off all my points in the final. Let's see here. That's why I have to teach this course again. Let's see here. X cubed. I'm an idiot. Plus, is it y squared? You guys you guys take this course once and you go on. Many of you. But I have to keep teaching it. Let's see here. Z beta partial x percent 2 alpha, right? And then plus we got 2y. Secant squared. Now there's some dangerous things I'm doing in this problem. I'm assuming you know how to differentiate tangent, which is dangerous, but I refuse to back off of that. Calculus 1 does come before Calculus 2, and Calculus 2 comes before this course, so there you go. So the partial derivative of beta e to the beta with respect to alpha, it is 0, or gyro, as my friend Tupomoy Sarkar used to say. Let's see here. Anyway, so this is gone. That's what I mean, of course. You can leave the answer in terms of the quote-unquote intermediate variables, which in this case are x and y. On the other hand, we have the symbolic chain rule kind of problem like this, right? Where I tell you that you're looking at a function of 3 variables. I tell you the x derivative and the y derivative at the point and the z derivative at the point are 11, 3, and 2, and I say calculate. What do I ask you to calculate here? Partial x, partial z. How do you do that kind of problem? Do you guys remember? It's been a little while. By the way, I'm disproportionately focusing this review session on the first part of the course, not because the final is disproportionately focused on that, but because we have spent a lot of time lately talking about the last part of the course. So I figure it's more useful for you guys for me to focus on the stuff that you're a little bit less fresh on. So we have this, yeah? we take the total differential of this. It gives us then the fx dx plus fy dy plus fz dz equal to 0. If I want to calculate partial x, partial z, I solve for dx. So this gives me that dx is equal to minus fy over fx dy minus fz over fx dz, right? And what was I asked to calculate? Partial x, partial z. So that's going to be this one. This will tell me what is partial x, partial z at the point. So partial x, partial z is going to be minus fz over fx at the point in question, which in this case is minus 2 over 11. Yes. You're like, you mean to tell me that you gave me 3 pieces of information here when I only needed to use 2 of them? Yes, I would do such a thing. Why would I do such a thing? To make sure you're not just randomly guessing one of 2 possibilities, yes. All right, here's the switching order of bounds problem I was mumbling about. Of course, on your test, I believe you had this in the form of a, what was it? Let's take a stroll down memory lane. I heard exponential, I think. I like that. That rings true to me. This feels like test 2, was it? Or 3? 3? 3? Yeah. These are all great problems, by the way.
Especially that one.
Especially this one. Huh. Now I'm starting to think it might have been Math Battle 3. Ah, there it is. Problem 6 on Math Battle 3 is another example of this type. Integrate e to the... Remember, integrate e to the y squared dy dx. So, I mean, you see something like this, even if I didn't tell you to switch the bounds, you know you have to because we don't know how to integrate e to the y squared, right? But if you switch to do x first, then the process of integrating the first integration may pull down something which then makes the u substitution happen, and that's what, in fact, exactly what happens. So I, look at what those bounds indicate, which is this integration region, right? Because they say that y is between 2x and 2, and that x is ranging from 0 to 1. So if I reorder that, I go from x equal to 0 to x equals to y over 2, which is the right. So that gives me this inner bound for x. And then the y ranges from 0 all the way up to 2 for that. So I change the integration setup from a type 1 to a type 2. And in so doing, when I do my integration with respect to x, e to the y squared is held constant, and it ends up pulling down a y over 2, which is super nice because then this is just a plain Jane u substitution, right? U equals y squared, and we can go from there. No one's named Jane anymore, so there's really little danger in using this expression. But anyway, there are no Janes here, are there? Just kidding, I know you're not named Jane. And any middle name's Jane, though. There could be some middle name, hidden middle Jane. No, your middle name is Jane? Interesting. Bold. Yes, go on. Your parents are very progressive. Did you have another question? Attendance has already been asked about. That's off the table. No? Oh, okay. All right. Anyway. But the one I was just looking at, where did I put that thing? No. Was it this one? Where did my final go? I don't know. I lost it. I've lost the final. the easiest way for me to get back to it is to go back to here and then go, there we go. All right. So, okay, so you guys, what would that, I think actually, oh, goodness gracious, I think that may actually be the same stupid integration region as the one we were just looking at. Oh, wait a minute, no. This is going from type 2 to type 1. This is actually genuinely different than the one. It's probably good for us to actually sort through this for a minute. So what are the inequalities suggested by that? Y over 2 less than or equal to x less than or equal to what? 1. And what else? I heard it, yeah, 2? Right. Now, this does not help me, but if I rewrite this as y equals to 2x, then I kind of understand it, you know? So we've got y equals to 2x. We've got x equals to 1, right? And we're going from 0 to 2. I guess that's the intersection point, right? So we're looking at, you know, this is the region of integration, yeah? So let's see here. We could also say what? 0 less than or equal to x less than or equal to 1. 0 less than or equal to y less than or equal to what? 2x, right? So this integration could be recast as the integration from 0 to 1, integration from 0 to 2x of cosine of x squared dy dx, which is ever so nice, because then that's the integral from 0 to 1 of 2x cosine of x squared dx, which we can make a u equals x squared substitution to do. Yep.
How do you know which side of that y equals 2x is? Why is it not the top triangle? Why is it the bottom side triangle?
Oh, because this says that this is, I mean, so here's a typical point in here. This is x comma y, right? And that x comma y satisfies these inequalities right here. So we're to the right of 1, and we're to the left of y over 2. I mean, this is also x equals to y over 2. That's how I know we're not. Let's see here. If I had had in the integration, I could have had the integration from 0 to 2, integration from y over 2. No. From 0 to y over 2. That, if I had that, right? If I had that, that would look like what you're saying, which is this one. See, because this would suggest 0 less than or equal to x less than or equal to y over 2. That would say that the y over 2 curve is to the right of the integration region as opposed to the left. There's a difference, yeah. Good question. Yeah. Moving on. Let V be the volume bounded by the coordinate planes 3x plus 2y plus z equal to 6. Suppose V has total mass m and mass density, variable mass density, right, alpha x. Find alpha in terms of m. Interesting. So what would you have to do? What do you have to do basically here? You have to integrate. We're asked to do the integration of what? So we need to take the triple integral over the shape. I'll call it E of dm, right? I mean, I would do that. I would calculate the total mass. Now that's the triple integral of alpha x dv, right? Because I'm given that the mass per unit volume is alpha x, so I want to integrate alpha x times dv to get the integration of dm over the volume, which would give me the total mass m, right? Then the question is, how do you set up that integration? Well, we're looking at one of these deals, right? And so this is the E. It's that sort of four-sided, every side's a triangle, right? It's not a tetrahedron, but it's a sort of an irregular tetrahedron, perhaps. What's this line here? 3x plus 2y equal to 6, right? This is where z is equal to 0, right? Can you give me these corner points? Two, 0, 0, right? How about this one over here? 0, 3, 0, yeah? What's the top point? 0, 0, 6, yeah. Okay. So the way I see it, 0 less than or equal to z less than or equal to 6 minus 3x minus 2y. If we look at this triangle right here, focus in on that. This is 2, 0, 0. This over here is 0, 3, 0. That's why this is x in my unfortunate drawing. It's going to get me into trouble. Let me flip that over. Ah! No, forget it. I'll just leave it. But I'm just going to have to tilt my head and squint a little bit. So this is what? This is y equals to 6 minus 3x over 2. This is, of course, y equals to 0. So if I think about a point going from here to here, I've got, 0 less than or equal to 6 minus 3x, 0 less than or equal to y, less than or equal to 6 minus 3x over 2. So that'd be my next thing. 0 less than or equal to y, less than or equal to 6 minus 3x over 2, which, of course, a civilized human being could write as, I'll leave it like that, to be uncivilized. And then how about x? What's x range from 0 to 2? So again, you can view this system of three inequalities as sort of sculpting this irregular tetrahedral volume from three-dimensional space, and that motivates me saying that this calculation would be done by the integral from 0 to 2, integral from 0 to 6 minus 3x over 2, integral from 0 to 6 minus 3x minus 2y, all of alpha x, and then let's see here what comes first. dz, then dy, then dx. There you go. That will give you alpha times some number, right, when you sort through it. And the answer, as I've stated the question, would be that alpha is equal to m divided by that number. Although I usually ask for m in terms of alpha. My wording here is strange to my taste. Yeah. Find the volume bounded by x squared plus y squared less than or equal to 1, and 1 plus x less than or equal to z less than or equal to 9 minus x squared minus y squared. How would you do this problem? First of all, I would try to visualize it. Basically, I'm looking at the cylinder, right? That's x squared plus y squared less than or equal to 1, right? And I've also got z between 1 plus x and 9 minus that, right? So 1 plus x is something like some sort of plane, and the other one is some sort of, paraboloid. So it seems to me what we're looking at is basically some sort of like, with like a, it's like a planar slice down here. But the larger point is that I think we could describe it this way: 0 less than or equal to theta less than or equal to 2 pi, right? 0 less than or equal to r less than or equal to 1. And my z, right, is between what and what? 1 minus x, which is what? 1 minus r cosine theta. And my other one is 9 minus r squared.
1 minus x or 1 plus x?
I forgot. Oh, plus. Sorry. My point to you is that this is pretty easy to like sort through in cylindrical coordinates, right? And then I just have to do the volume is the triple integral of dv, right? Over this shape. I'll call it E again. And so that'd be integral from 0 to 2 pi, integral from 0 to 1, integral from 1 plus r cosine theta, bless you, 9 minus r squared. And then what's my dv? We've got an r dz, dr, d theta. And you just have to do it. Work it out. Any questions?
So we wouldn't be separated from the upper spherical piece then?
No. Because in arbitrary, I mean, this set of three inequalities describes a typical point, you know, x, y, z with cylindrical coordinates, you know, r, theta, z. This straight describes where that is without ambiguity. Yeah. We could try to describe this region with spherical coordinates if you'd like. No. 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 I mean, it's kind of a good exercise, though, to try to describe. I mean, this is probably a good exercise for us. Let's try it. So suppose we'll just look a little bit simpler, but let's look at this right circular cone, all right? Right circular cone, height h, right radius r, right? Right circular, not cone, I said cylinder, not cone. Describe this in cylindrical coordinates. Not a big deal, right? In cylindrical coordinates, what do you got? You got 0 less than or equal to z less than or equal to h. Your theta goes all the way around. And how about r? Right? So in terms of cylindrical coordinates, it's shockingly easy to describe a cylinder. Okay, that's actually not surprising. But what if you asked the dastardly question to describe this cylinder in terms of spherical coordinates? How would you describe this cylinder in terms of spherical coordinates? I'll start us out. 0 less than or equal to theta less than or equal to 2 pi. Haha. I picked the low-hanging fruit because it's obvious we go all the way around, right? But then what? You gotta think about it, right? I mean, if I draw, it's helpful maybe to draw this sort of cross-sectional picture, right? So if this is z, and let's say that this is, you know, y or x, whatever. But it could be x, whatever. Some kind of that sort of picture. If you look at that, there's obviously two cases, right? So this one versus this one. See, because in case 1, you have 0 less than or equal to rho less than or equal to whatever that is, right? But in the other case, you have 0 less than or equal to rho less than or equal to whatever that is, right? And how do you figure out those maximum spherical distances? And it's fairly clear, though, that this should be for what? Phi 1 less than or equal to phi less than or equal to pi over 2. And then the red one should be for what? 0 less than or equal to phi less than or equal to phi 1, whatever that phi 1 is. I mean, we could figure out phi 1 pretty easily, right? Phi 1 is this guy.